Hey, okay, tell me about yourself, Babu.
Good evening, sir. Myself, Venkan Babu. I am from West Godavari, Andhra Pradesh, sir.
Okay.
I've completed my graduation in BTech from EC department, and I have completed my graduation from Vizag Gitam University, sir. I am a 2020 graduated person, sir. Okay, from then I completely focused on my basics, and I've completely focused on my electronics and digital topics. And at 2024, I joined
Okay. So you said you have done your BTech from your which college?
Geetham, sir.
Okay, okay. Geetam. So tell me about your BTech project.
In the BTech, I have done my project uh, in the field of uh, so sorry, I'm not recollecting that. Sorry,
Man,
sir.
it's your BTech, man. Your first project, right? I mean, it's the most important.
Yes, sir. But
Fine. Okay. So tell me what you learned in your training, that Sumedha IT or whatever it is. So you are Sumedha IT, right? You joined Sumedha IT.
yes, sir. Yes, sir.
Yeah, yeah. Tell me what you did or what you learned in your. Just brief me now. Later we'll go in deep.
Okay, sir. There we have started with basics, sir. It's they have dealt me on digital topics, and later they have focused on fundamentals at diodes, MOSFETs, BJTs, and later we have entered into core topics like synthesis. We have started with, and later STA, and later into PD, sir.
Okay. Tell me what you did in your PNR.
Yeah, in the PNR, we have started with the floor plan, uh, and we have gone through the flow of the PD. It's like from floor plan and then placement, and then okay. In the floor plan, we have power plan also, and then we place placement, and next CTS, and then routing. And later PV checks, physical verification. In that stage, we have not completely focused, but from floor plan to routing is what we have learned there, sir.
Okay. Tell me what you did in your flow plan.
In the floor plan, the very first thing we have done was like we have given the aspect ratio of the core, and the core shape we have given, the dimensions of the core, and then uh, we have given the offset from core to die area, and then we have placed macros in it, placement blockages. We have placed uh, ports at the uh, die region, uh, and then we have gone through power plan where we have placed rings around the core, in between core and die area, and then we have placed stripes from rings to the um, uh, we call uh, uh, rails, power rails, which from there the power enters to the standard cells.
Okay. So in your flow plan, you said you defined the aspect ratio. How did you do it?
Uh, I have given the width to length ratio.
Where?
It's in the through GUI we have done. So the GUI we have done, that's in the cadence tool,
Hmm.
Innovus.
Where? Like how you did it? So what are the steps you followed?
Uh, yeah, in the uh, after dumping all the files in the tool, we come into GUI. In that GUI, we give in the floor plan. Uh, Under floor plan, we will have certain options like aspect ratio, all these things. In that, we have given the aspect ratio, sir.
In floor plan? Sure about your answer?
Sir, actually, I'm not completely sure, sir, because uh, mm, yeah,
See, you are going to be a PD engineer, right?
yes, sir.
So how can I expect that you are not sure? Like, see, I assume if I'm running a company now and I want to work on a project, I need a person who will be working on the project. And if I'm, why should I hire you if you are not confident in your answers and if you are not sure about what you have done,
Yes, sir.
right? I'll hire the other person. There'll be, if I say that there is an opening for a PD job, I'll get 100 resumes to which I need only 10 candidates. I'll leave you and take the other one, right? Okay, good. So, okay, aspect ratio. Then what you did?
And then the shape of the core, sir.
Okay,
So
what was the shape of it?
basically, we have a rectangular shape, a T shape, and we have a U shape also. And we give the dimensions of each side of the shape of the core.
Okay.
And, so, and then we
Then
mention the offset from core to die area.
okay,
Yes, sir.
that's it.
Uh, and utilization ratio also we'll mention, sir.
Okay, what was the utilization ratio?
Uh, it's uh, during floor plan we mention the tool that we make the tool to use this much amount of area and left for the next stages.
Yeah, that only. Which one? What is the percentage numbers?
Um I'm completely not sure that maybe around it's around below 50 sorry 7 yeah below 50%, because we need more place for the cells to be placed in the placement stage.
Okay, so you did your aspect ratio finalizing in your floor plan stage, and that's it, right? That's what you did it, and then you defined the core and die area. That's it, right?
And we and then we come to the placing of the macros, sir,
Okay.
and where we place macros according to the macro guidelines. Uh,
Okay, tell me about your macro guidelines.
okay, sir. Um, we need to place macros around the periphery of the core area. The
Hmm.
reason is if we place macros at the center, um, that needs more routing. It's like actually the macros are power greedy. So if we place at the center, the routing for power becomes more length. We need more. That becomes more length of routing. So more drop of voltage happens. Um, and also, if cells place around the macros, if macros place at the center, then detouring happens. So that's the reason we place around the boundary of the core, and the pins of the core has to be placed around towards the center of the core region. The placement of macros has to be done according to the fly lengths. So first priority has to be given to the macros. Uh, the macros who having communication with the ports, and the macros having communication with themselves, that is macro to macro. and the macros having communication with the standards. Maybe that is not right now. Yeah. We have to give priority to the macros that having communication with the ports first. Okay, and we need to create minimum channel between these two macros. If not, congestion happens, and also we need to place key port margin around this uh, macros so that no standard cell sit near the macros. If at all we haven't given the this key port margin, the cell sits and the congestion happens. That is the the amount of tracks needed, the amount of tracks required becomes more than the number of tracks available. That's the reason why congestion happens, uh, yeah, so these are the guidelines for the macros placement.
Okay, assume you have placed a macro which is at the core edge only, that is at the boundary around the boundary, and one of the standard cell corresponding to it is sitting at the other edge of your block. So why it might be like that, and what would you do to make them sit together?
The cell which having communication with the macro is sitting beyond this macro, you're saying, right, sir?
Assume you are having the macro at the left top corner, and the cell that is communicating to this macro is sitting at the right bottom corner.
Okay, sir.
So what would be the reason for it, and why would it sit like that?
Maybe at the initial placement this happens, and in the final placement this may go near and may sit near the
Even after final placement, even after final placement.
even after final placement. That may be due to having no space near that region, maybe.
It does have space, but still it is going and shedding there.
Okay. That is sitting there. Oh. If it is only one cell, maybe we can place that manually, I think, sir.
Okay, but assume there are bunch of cells, 15, 20.
If that is the case, then we go for the creation of bounds.
But you are trying to go for the solution. But first try to understand or try to answer like why is it happening? Like what is the reason?
Okay. I got it, but so is it there like it gives more priority to the cell to cell communication than cell to macro?
No. There is a one particular reason why it would have been placed like that, right? So your macro is sitting at the left top and the cell is sitting at the right bottom. So if you have done multiple trials of macro placement, you would understand this. Why it might be. So what are the other guidelines that this is going to follow, the tool is going to follow? Why is it placing like that? Just think.
Okay.
Yes. Sign communication with the ports. So now you tell me what would you do to this?
So maybe I will do floor plan again. It's like
So instead of trying to place macros on side and then looking for the cell sitting like that, what else could you have done at the first place only?
hmm,
What you would have done so that this would have been like fine or best?
so maybe having complete command on the fly lens.
First thing is you have to look into the fly line so that your this whole part is done. So you have to analyze based on the fly lines. So what does your fly lines? How does it work?
It says what are all having communication between.
Hmm. I- Sorry, come again.
Yeah,
What it
it's like
says?
the fly lens says what are all the cells or the macros having or the between port to between port to macro or macro to macro, all these communications details will be set by this fly lens.
So if that is shown, what could you have been done so that you would understood this? Like,
Okay. Hmm. So maybe I have said before, like we need to give more priority to the fly lens having communication within port and the macros and macro
so
to macro.
that is what I'm asking you. So what mistake happened in this scenario?
What mistake have been?
You are say the macro sitting at the top corner and your cell sitting at the right top corner. So the reason you found out that cell is sitting because the port is near to that one, right? So what went wrong here? What mistake was happened so that this scenario you landed in?
Maybe we need to consider all these three elements, that is port, cells, macros together. If these three having communication, we need to place them together, I think.
So the main reason is you should have done the fly lines properly, right?
Yes, sir.
That was my question. Okay, fine. Go ahead. Next, what you did after placing the macros?
After placing macros, we have entered into uh, uh, saying the tool that these layers is follow this kind of routing direction and the so we have mentioned which layer will be in the vertical and which layer will be in horizontal. So we have mentioned that to the tool.
Repeat it again. Repeat it again.
We have mentioned the tool that with which particular layer routing direction will be vertical and which particular metal layer follows the horizontal direction routing.
Okay. Then.
And then we have placed few physical only cells. This can happen after the power plan also, but sometimes we can place the few cells, physical only cells before the power plan also. So
Okay.
that's
Fine.
what we have done, and then we enter into the power plan. That's complete together was done as a floor plan.
Okay. Fine. So you can you brief me about what are these physical only cells?
Okay, sir. So these physical only cells are comes under the standard cells also, but they don't participate in the logic functionality because not because basically they don't have the input and output pins. They have only the power and ground pins. Um, um, we place this during to overcome few issues like latch-up issue, and to protect particular cells, we place end cap cells. To overcome the latch-up issue, we place well tap cells, um, so as to preserve the cell from getting damaged while giving logic 1 or logic 0. Uh, we place tie high, tie low cells without directly connecting to the VDD or ground. That's the one use, and we also place yeah, filler cells where to fill the gaps that were that will happen after placing all the cells. uh, After placement stage, we place these filler cells basically. uh, we have decap cells where decap cells are like they act like a backup power. It's like when a few of the cells uh, so yeah, let's say we have a cell where it's switching from 1 to 0. So during this process, uh, that cell which having NMOS and PMOS internally can come to on state for small fraction of second, sorry, small fraction of time. That leads to more consumption of power, and that leads to shortage of power for the next cells that have placed next to this cell. So we place decop cells periodically at some places so as to compensate this drop of voltage for the cells next to this cell which has dropped the voltage. And so these decap cells are like charging will happen, charging and discharging will happen. The main use is to supply a backup power. That's what the use of decap is. And yeah, these are the few physical only cells.
So can you explain the latch-up effect?
Okay, sir. Latch-up effect. Yeah. Uh, in olden days, in the like in the days before, the cells used to have VDD connecting to the N well and ground connecting to the P substrate. This kind of thing used to happen in the previous olden days, but later stages, this was not made connecting internally for the same standard cell itself, because that connecting of VDD to sorry, N well to VDD and ground, so P substrate to ground will make the cell have much more area. So what I have done, like they have separated this VDD connecting to N channel and ground connecting sub TP P substrate. So yeah, sorry, because of
So
the
listen. So what is the reason for getting a latch-up effect?
sorry, the reason for getting latch-up effect is because of the CMOS internally the parasitic transistor will form, that is BJT will form, PNP and NPN, and
Why
if
does it form? Why does that form?
the structure itself is a more helpful for creating that kind, because if we see the CMOS structure, um, why it happens means because of the well resistance on the substrate resistance. If very small fluctuation of voltage happens, the current passes through this, and the feedback happens, and more heat happens, and then the damage to the cell happens.
Fine, but the answer is not convincing. No, you're missing the main point.
Mm, yeah, uh, that leads to short circuit between VDD and ground.
It will create a short circuit between.
VDD and ground.
Okay, so what does it happen?
So if that is what happens, a path between that ground VDD terminal to the ground happens, where lots of power driving happens, thereby the damage in the cell happens. So more heats and then damage.
So what we can do, like because of that, what we can like how it can be avoided and all.
Because of that, the main reason for this short circuit between VDD and ground is like because of this parasitic transistors getting created in it. So for that, we need to increase the resistance between VDD and the base of the first transistor and ground to the base of the another transistor, that is NPN or PNP. So this well resistance and substrate resistance, if we made increased, then the resistance between this VDD and ground will be more. The short circuit between VDD and VSS will not happen. For that, what we do is like we will connect NBEL to the VDD and P substrate to the ground with the help of this physical only cell called well tap cell.
Okay, fine. Now come to the placement and explain me about placement stage, what you did and what all challenges you faced.
Okay, in the placement stage, the complete placement stage comes under 5 steps. That is initial course placement. Uh, Second is the high fan out net synthesis, and the third is the initial optimization. Fourth is final placement, and fifth is final optimization. So the first thing, initial course placement, where the tool tries to place all the cells in it. Its main aim is to decrease the length between each cell as much as possible. Its main goal is to place the cells with less interconnect length. Uh, Sorry, the distance between cell has to be as small as possible. In that goal, it places all the cells in the core region. The second thing is high fan out net synthesis. We have some asynchronous signals called reset, preset, clear signals. So these are the signals which have high fan out. So these are the signals which have high fan out. That is, this signal has to connect all the reset pin or a clear pin of all the flops. That means in the one uh, source is having lots of connections to the flops. It's like we have lots of fan out. So we have, and our goal is to maintain the DRCs like um, mm, what we call min tran. So as to preserve this min tran, we will what we do is like we will buffer this high fan out net synthesis. So the tool, the second step, what tool we do is like high fan out net synthesis. The high fan out net synthesis itself, it's called buffering this high fan out things. So as to preserve this DRC input run. And here itself, another thing happens is like scan chain reordering. So scan chain reordering is nothing but in the synthesis after getting gate level netlist, we'll give that to the DFT team where scan chain. So it's like these are the team where scan uh, file inserting into this gate level netlist happens, where the flop converts to scan flop. So in the placement stage, this scan flop uh, uh, chain uh, reordering happens so as to reduce the wire length. So that's the main goal of that. And next, the third step is the initial optimization. The goal of the initial optimization is to reduce the WNS, TNS as much as possible. And the final placement in the fourth step is the final placement, where the tool places according to the so as to reduce this timing that has left in the third step, that is initial optimization. And the fifth step is the final optimization. Here the complete goal is to optimize with respect to congestion, power, area. So these are what we call quality of results in the placement stage. So as to perform all these 5 stages, we need to first of all design. We have to give some inputs to the tool. The very first thing before going to the placement, those are called uh, initial placement uh, design requirements and flow design requirements. They are the first thing is we need to configure uh, what we call scenario. The scenario with what we are working with, we need to first configure that. If we don't configure particular scenario, the tool tries to optimize for all the scenarios. It takes lots of time. So we need to make the tool to stick to particular configuration, sorry, for to particular scenario. So we need to configure that particular scenario. The first thing at the very first thing we have to do in the placement is that's the thing. And the second thing we need to do was like scenario.
Yeah, good.
Yes, sir. Uh, Sorry. Yeah, we need to enable the SPG flow. So this is related to the ICC too, because if we perform a compile ultra with the SPG in the design compiler of Synopsys, so if we perform in the placement according to the gate level networks that have come from the design compiler in the ICC2, what they do is like they will enable this SPG flow, where this saves the time, like in the compile ultra SPG command itself do scan chain reordering as well as the high fan out net synthesis. So in the placement stage, if we enable this, lots of time will get reduced. So,
Yeah, tell
but
me what will happen with your PlaySoft settings.
PlaySoft, uh, yeah, PlaySoft, yeah, the tool performs all these 5 steps that I have briefed before, sir.
Tell me what are those.
Yeah, these are the initial course placement, the high fan out net synthesis, uh, the initial placement, final placement, and final optimization.
Tell me, brief it. Initial placement, everything.
Okay, initial course placement. The main aim of this first step is to mm, um, so with the very first step, the tool tries to place all the cells in the core region, keeping in mind that the length between, so the interconnect length between these cells has to be small, as much small as possible. Accordingly, it will place the cells on the core region. And the second step is high fan net synthesis. uh, we have a few asynchronous signals called uh, reset, clear, uh, reset, clear, uh, set. All these asynchronous signals will have high fan out thing. So as to have DRC, there's minimum tran. What tool do is buffering. So this buffering of high fan out thing is called high fan out net synthesis. That's the second step. What in the placement stage happens, and also scan chain rerouting happens. The main goal is to reduce the wire length again. And the third is initial optimization, where the tool tries to reduce the WNS, TNS as much as possible. The left thing, that is WNS and TNS, what the tool has left will be done in the final placement. And the final optimization stage, the tool tries to optimize with respect to congestion, power, area. These are the things three we call quality of results in the placement stage.
Okay, so now tell me, assume we'll go for a scenario now. Assume you have made a placement and all, but after the end of placement stage, before open you go to the CTS stage, you are seeing a lot of congestion in your block. What might be the reason, and how would you resolve it?
Okay. The reason for congestion during placement is like uh, the cell the cells getting placed very close. That could be one reason, and pin density is more. That the first thing we call as a max cell density, and the second is the if you have more pin density also congestion will leads. And third, if you don't place placement blockages, that can lead. And uh, uh, yes, so these are the few reasons for the reasons for getting congestion.
Okay, what would be your approach to face these challenges?
We need to split these cells as uh, yeah. For that, sorry, we need to place placement blockages. The first thing, and we need to increase the placement and congestion efforts, and we need to enable mm, pin access. Sorry, pin access check. This is this says if any of the pins got blocked. If
Wait, Babu. Let's go one by one. I'll ask a question directly. So the question is now, assume you have placed this placement and all is done. You have lot of congestion there. So what will be the main reason for congestion? You said that one of them will be placing of cells closely, right?
yes,
So now I want. So what would be the solution if you place the cells widely? It would be fine, right?
yes, sir.
So, how will the placing of cells closely cause the congestion?
Yeah, if the cells got placed very near, uh, the requirement of more tracks happens at that particular region, where that particular region may not compensate the requirement of tracks for those number of cells.
So, what will you have to do for that? So, how will giving a space between the standard cells make the routing tracks? How will it do?
Yeah, the requirement of tracks may be less or equal to the available tracks. Then if the cells got placed not very closer, then we may not enter into congestion state.
Okay, fine. So, how will you enable these tracks? Like by just providing spacing between the standard cell?
No, but it's a placement is a iterative step. Accordingly, we will check if the congestion is very bad. Then we go for the placing of placement blockages.
So, just by providing placement blockages, you will resolve this spacing issue.
Oh no, no, and we need to do. Uh, we have few cells called um, uh, AOI and OAI cells will have more pin density. So what tool you do is like it will restructure these pins without changing the functionality. Thereby, the crisscrossing may reduce so that congestion will get reduced.
Okay, fine. But that won't be sufficient, right?
Yes, but yes, sir. One.
Fine.
Uh,
Okay. Tell me about CTS. Let's talk about it.
okay, sir. CTS is the stage where routing of clocks to the flip-flops happens. The main goal of the CTS is to balance the skew, reduce the insertion delay as small as possible, and we need to reduce the crosstalk. Mm, we need to one second, sir. Yeah, the power consumption has to be less, uh, and yeah, these are the goals of the CTS, and uh, we pass few constraints during this stage, and those are like uh, uh, uh,
Yes. Tell me.
yes, sir. Uh, um, Here in the synthesis stage, we will give skew as the parameter and in the uncertainty. So uncertainty is comprises of skew, small extra margin, and the jitter. But when coming to the CTS, the clocks are propagated. Like we have real clocks in us in the tool. So we have to nullify this skew in the uncertainty. So so this is the amendment we do in the CTS stage, and and uh, yeah, we have to enable clock tree cells, clock tree buffers that we have.
Okay. Why
Uh,
can't you use a normal buffer? Why you only need to enable a clock tree buffer?
okay, in the clock tree buffer has a few characters like they have 50% duty cycle, and they have more drive strength than the normal buffer.
Okay. You mean to say that it has more drive strength than normal buffer?
Yes, sir.
Just
And
because it
mainly,
has 50% duty cycle.
yeah, 50% duty cycle is sure, sir. They have 50% duty cycle.
Fine, but the reason what you are linking is not so fine. So are you sure about it? Like having a 50% duty cycle will help in driving higher drive strength. So even you have a normal buffer with higher drive strength, why can't you use them? But why are you using clock buffers here?
Uh, mm, Maybe so. Maybe main reason was 50% duty cycle, sir.
Sure about your answer?
Um, Not completely, sir. I'm thinking it's the 50. One reason could be this, and maybe it has few other reasons. I'm not recollecting them.
Okay, fine. So, Azim, now you are going to build a clock tree tomorrow in your block, in a practical block where you are having a length of your clock source to clock sink is very huge, very long. So, what would be your approach to resolve it?
If that is what the case, um, so we'll place a clock buffer, sir.
Okay, but will it help?
Uh, yes, sir. Our motto is to reduce queue, and we need to reduce the insertion delay. So delay of anything can be reduced by normally buffering. So delay of anything can be reduced by decreasing the input RAM and decreasing the output cap. So if we made buffering, the length of interconnect get reduced, thereby the resistance of interconnect reduces, thereby cap reduces, thereby delay get reduced. So the goal of CTS can be met with this buffering of yeah, buffering can happen. If that is so, then we can
Okay, fine. Brief me about routing.
okay, sir. Routing is the stage where routing of the signals happens. The main aim here is to uh, reduce detour as much as possible. The completely four stages we have, oh, sorry, three stages we have here. The first is the global routing. Second is the track assignment. The third is the detail routing. The first stage uh, mm, global routing. Here, the tool tries completely divides the whole routing area into GRCs, where the GRC is the thing which gives the available routing source. Thereby, we can the tool thereby it comes to conclusion that if the routing happens here, the congestion may lead. If not here, if since it has less more available tracks, if routing has done with these available routing sources, congestion may happen less. So based on this, so has to come to these conclusions. What tool do is like it creates GRCs. So GRCs uses so this kind of uh, uh, getting into conclusion can be happen with this because of these GRCs. Here, uh, 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 here zero with lines of routing happens. Here, routing shapes will not happen in this stage. In the track assignment, assigning of net to a particular track happens. Here in the stage where shape of metals is according to DRVs of the DRVs happens here. And the third is the detail routing. The main aim of this is to meet the DRVs. Like it has to meet the manufacturing rules.
Okay, what do you mean by NDR?
Oh, NDRs are the non-default rules. This mainly happens in the CTS stage where to mitigate the crosstalk that happens because of placing clock route interconnects. If these are very close to each other, the capacitance between them may get increased. Because of that, crosstalk noise and crosstalk glitch may happen. So because of that, NDRs is like we can increase the width and the spacing between these interconnects.
Okay, so what would be happening? Like, what would be the effect if you are not following NDR rules?
Yeah, if we don't follow, that leads to crosstalk in the CTS, sir.
Only crosstalk in CTS. That's it.
Crosstalk and so as to preserve the signal integrity, electron migration issue. So to have a better signal integrity, also we use the NDRs and so as to compensate the electron migration, also we use the NDRs, sir.
Okay, but Any other issues if you are going to are you going to face with respect to this, like for not following NDR?
Hmm. Hmm. So these are the reasons I'm collecting. Maybe there may be few other reasons. Right now, I'm not unable to recollect them.
Okay, fine. So, what would you brief about, or what would you talk about the ECS stages?
Okay. Yeah, so I have forgotten to say this, sir. In the spare cells are those also comes under the spare cells are those which come into usage during the ECO stage. We need to place them group of cells like few logic gates and or all the few that we have used during the logic implementation in the placement CTS, all these things. So those are the particular cells we place at periodically few places on the core area. So the main reason for placing this is if after uh, complete PNR, if any few timing issues or any if any meeting of slag is not happening with some particular timing path, then without going to the scratch, the at that particular stage only we'll nullify these issues with the cells that we have placed at that particular region. So this is the stage where we call ECO. It's a engineering change order.
So, you want to do much more than this in ECO? Is it only this much? Have you done anything in ECO stage, or just a brief idea about only it, like no practical hands on it?
Sorry, sir, I have only this much of an idea on that. I haven't done any practical hands on that.
Okay, fine. Uh, okay, that's it. Let's end the interview here. Okay.
Sir, please give me any suggestions so that I can improve on that.
First thing is you have to prepare more. Industry demands a lot, and the thing is very different in the industry and what you all are learning. So the training institute, what they teach you is completely like you are at least 5 years behind than what industry is now. So you have to learn Linux, you have to learn Shell, you have to learn analysis, timing analysis. The major part of the game is itself in the ECO, because most of the company, all the top companies have already set up a flow where you don't need to do much efforts from synthesis till routing stage. Every game begins after routing, that is at the ECO stage. Only thing you have to worry about is proper aspect ratio, finalizing macro placement. These are all from flow plan. So in some cases, even some companies give you the macro placement also ready and ports also ready. Only thing is you have to make them legally placed and proper blockages. So that's where you have to work in a flow plan. In placement stage, you don't need to do much. You have to handle the blockages, and you have to make sure that the cells are spread. You have to learn about cell padding. You have to learn about adding placement blockages in a particular way the cells get spread, and you have to make sure that you have to worry about drops, IR drop, and EM violations. So these all things comes, and then congestion hotspot numbers. So in CDS, yeah, there are multiple things. Very small way you are going to work in these areas, placement, CTS, and all. In CTS you need to know to build a clock tree. So every cell in your block needs to know how much you need to know that how long this routing link takes. Is it okay? Will it meet the clock skew, clock latency? Everything you need to know. Or is it going to meet the setup hold? So just by numbers, you should be able to identify that this is going to work. So this one thing you have to learn. And yeah, there are a lot of other things, but for now, these things you learn. So you have to upgrade yourself. You need to learn in depth of all the things. You should be confident about what you are going to answer, because otherwise it is really really difficult to survive here. Okay. So
sir.
learn that, prepare well,
Okay, sir.
keep it going. But yeah, do one thing. What I can suggest is that if you are not in job anywhere right now and if you are sitting at home, there are plenty of websites. Go and search VLSI websites. You will get uh, a number of websites. Mark 5 of them. I think I have shared these websites to Rajat, I guess. So you might ask him, he might provide you the website link. So just go through each website, study the floor plan topic once a day, like one topic a day. So refer all the websites, try to make a point, notes about yourself and learn. If you get any chance, go and try to work on the tool, be it Cadence, Syllabus or Fusion Compiler. So understand how the flow goes and everything. So learn the scripts. I mean, learn to try to understand all the scripts and learn them. I think that would be enough for you. No? Okay. Because when you go to the industry, service based companies usually they usually put you with an experience into the industry. So once when you go with, they'll put you fake experience. So once when you go with the fake experience, it is very difficult for you to sustain there. So you need to know at least a bit, because you are mocking there that I know I am experienced, but there going and handling is really difficult, right? So do it. Okay.
Okay, sir.
Fine.
So ECO stage is very important, is what it's like.
Yes, yes, yes. The game changes are at ECOs. See, assume you are having a very very easy block where you have an area and no need to work on the uh, constraints. Like, I mean, no need to work on the power constraints. You don't need to worry about the power. Then it is easy. You can just finish all the things from flow itself. But
Yes,
if
sir.
you are working on a block which is area constraint, power constraint, then a lot of things need to be done in ECO.
Okay.
So that's what it is.
Okay, sir.
Okay.
Okay, sir.
Fine. All the best. Okay.
Okay, thank you, sir.
Okay. Thank you.